So in case of spring pendulum, so the time period of a spring pendulum, we know that K is nothing but the force constant, M is the mass of object, so T is equals to 2 pi square root of M upon K, and this spring, obviously the object mass, you just do to and fro motion, so its time period T is based on your force constant of spring. If I change the spring, the time period also get changed, and again it depends on the mass of that object also who is performing that your SHM over here. So what that Hooke's law states, the force needed to extend or compress a spring by some distance, so that linearly with the respect to that distance. Yeah, so the restoring force, obviously the more you want to stretch, the more you want to apply the need to apply external force. So that K is a constant factor, characteristics of the spring, X is a small compared to the total possible, obviously that deformation of the spring. So that is what we can say about your Hooke's law for this particular case. So this is your vibration of your loaded spring. So in that case, when the spring is either compressed, yeah, so for this particular case, stretched through a very small distance from the mean position, a restoring force it acts on it, F is equals to minus ky. If a mass is suspended from a spring, then equilibrium, you can write it down that mg is equals to kl. Yeah, and again based on that, so if I now connect the two springs of different spring constant in your series combination, then what is the value for that your spring constant? So 1 upon k equivalent is equals to 1 by k1 plus 1 by k2 over here. So for this particular case, so obviously I will say that the resultant extension x is equals to x1 plus x2, f is equals to kx. Yeah, so f upon x1, yeah, f upon k1, so plus f upon k2. So definitely this will be nothing, the resultant force 1 upon f. Yeah, so obviously in both the cases the force acting is same, so that is what we can say that, which is your f. So ff get cancelled, so 1 by k is equals to 1 by k1 plus 1 by k2. So this is how we can calculate the equivalent value for that your spring combination. So that is 1 by k is equals to 1 by k1 plus 1 by k2, and the same thing we have just put it over here. So that is your t is equals to 2 pi in bracket m upon k. So this one actually you can write it down, 1 upon that is k equivalent, obviously k1 k2 upon k1 plus k2. Just put down this value over here, and which will give you the value for this time of period of system t, that is when the springs is in series. So this is the expression which we have got when the springs are in series. So where the k equivalent, we just simply found that 1 upon k equivalent is equals to 1 by k1 plus 1 by k2, and then we know that t is equals to 2 pi square root of again m upon k. So now what we have seen actually for this case, so I just written that x is equals to x1 plus x2, the elongation produced in each individual spring is different. Yeah, so obviously that is x is equals to x1 plus x2, then your f upon k, obviously the based on the value of your, although you are applying the same force but which will result into the different elongations. So that's why we have written that x is equals to x1 plus x2. Now what will happen when the springs are connected in parallel? So let's say these two springs are connected in parallel, or either you can show in this way also. Yeah, so for example, and the block has been connected over here, and you're applying the force in the downward direction. So what will happen for this particular case? Again, the spring constant, we know that f is equals to minus k into x over here. So for this particular case, the total force is nothing but your f1 plus f2. So for this case, again I can write it down, that is your minus k1 x minus k2 x the elongation produced in both the spring is same. Again this is K equivalent, which is, you can take the minus sign common, x, that is K1 plus K2, and again further I can write it down. So this is your x, yeah, so definitely this is your F, which is equals to K into x, x get cancelled, and the magnitude wise you can write it down, which is K1 plus K2. So that is the equivalent value for your spring constant. So you can say that the same force, so although you are just connected these two blocks, let's say either you can represent it in this way also, you can consider any case, yeah. So this is how we are just going to connect either them in parallel, so which is possible in any of the configuration, and I will just simple apply the force. The same force will act on both the blocks, so that total force is nothing but your F1 plus F2, which is minus K1x minus K2x, x get cancelled, and you can write it down K equivalent is equals to K1 plus K2.